Science 757, Rheology, H.H. Winter, Lecture 12A. The viscoelastic behavior of a polymeric liquid and polymeric solid is given by a single material function, and that's the relaxation modulus. And we would like to be quantitative. We would like to give numbers describing the relaxation modulus, and today that's the subject of the discussion. So we start with the Boltzmann equation as discussed last time. You can see that the stress is completely described by the strain history and a material function. This material function is the relaxation modulus. And if you know this relaxation modulus, then you can calculate the stress in arbitrary shear flows, extensional flows, or any flow as long as the strain is small. And those can be steady flows or transients. You can describe all the time dependence. So this material functions is characterizing the material. From a molecular point of view, it's a measure of the molecular mobility, this relaxation modulus. Now, typically, this relaxation modulus looks like this. It's temperature dependent, but it's also very time dependent. So at a constant temperature, we would plot the relaxation modulus with a flow regime at long times. If we wait long enough, the material can really relax and flow. And then the so-called entanglement regime, where the material has a plateau type region, and then the transition to the glass and glassy value up here. The plateau modulus is in the order of 10 to the 6 Pascal, and the glassy region is about 10 to the 9 Pascal order of magnitude. And you should remember those values. That's very important. So what would be the characteristica of a modulus as drawn here? One characteristicum would be a continuation of this relaxation behavior of this region 2, and this value is the so-called plateau modulus, Gn0. You should have a number like that. And then there is a characteristic longest relaxation time for the material, a breakpoint in that system. We should measure that also. And then there is a shortest relaxation time for the plateau region, or you could say that characterizes the transition to the glassy behavior. If you observe your material at shorter time scales or at smaller length scales, then you will observe the glassy behavior of that system. Those three parameters are needed for the elastic behavior and for the flow region. And then some more information is needed for the shape of that curve. So I will come back. The shape of that curve depends on the polydispersity, branching, and molecular details. So you have to include that. So this is what we are looking for. That's what we would like to describe quantitatively. The relaxation spectrum, let me write this down here, is defined from the relaxation modulus. We would take the relaxation time spectrum, and in the continuous case, continuous fashion, you would say that the relaxation modulus is given as an integral over the relaxation spectrum, relaxation time spectrum lambda, h of lambda, times e to the minus t over lambda, d lambda over lambda, and this is integrated from 0 to infinity. We're integrating over all relaxation times, and lambda are the relaxation times. The result of characterization of the material here in terms of this h of lambda would be a curve log h, say, over log lambda is some decaying function for the transition to the glass. And then there's something for the entanglement region or the plateau type region, and then there will be a transition to 0. And somewhere here will be the longest relaxation time of the material, the cutoff. So that would be the continuous representation of the spectrum. The discrete form of the relaxation spectrum is given by the relaxation modulus, G of t. And this is given at sum of relaxation modes. Now, a single Maxwell fluid would, or a single relaxation mode as described by the Maxwell fluid, would relax in an exponential fashion. And the relaxation would be given by a front factor times an exponential function e to the minus t over lambda. That's the type of relaxation for a single Maxwell mode for Maxwell liquid. Now, in our polymeric liquid, we will represent, or polymeric solid, we will represent the relaxation by a sum of relaxation modes like this. So we have a sum where I goes from 1 to n modes, and the front factors depend on the specific time. So gi, lambda I are our parameters. Gi, lambda I, for I being equal, going from 1, 2, and so n. Those are the parameters which we should know to quantify the relaxation modulus. For modeling calculations, it's enough to know the relaxation modulus. But very often we would like to know the relaxation spectrum. It's a long-standing problem to calculate and to determine the relaxation spectrum. Now, if we use the discrete form, then we automatically have the relaxation spectrum given in a discrete form, where we would say the spectrum is just gi times the Dirac delta function evaluated at 1 minus lambda over lambda I. Now, this delta function is 0 over the whole range except where lambda is equal to lambda I. So with that, you're picking specific modes from the overall range, and I is again going from 0 to infinity. So in the discrete representation, we have the relaxation modulus and the relaxation spectrum simultaneously calculated. Later on, we will look at the possibilities of converting the continuous spectrum to the discrete spectrum and vice versa, to go back and forth between those two spectra. The central role of the spectrum is shown here. We would need the spectrum to determine the relaxation modulus and then do modeling calculation with that. That's good enough. But with that spectrum, we can calculate all the linear material functions in Ferry or typical books on linear viscoelasticity. So again, that's a complete description of the material behavior. It's also related to molecular theories, which use arguments, first principle arguments, to derive the stress and the relaxation behavior of materials. So that spectrum is closely related to molecular dynamics. And it also should be related to molecular structure. For instance, changes in molar mass distribution should be notified, should be seen in changes in the relaxation spectrum. And we could, for instance, have a sensor measuring the relaxation time spectrum on a polymerization reactor, and then correlate the state of that reaction with the rheological measurements. So that would require a so-called blending rule. Now, the relaxation spectrum is described from first principles by the Gauss model and also by the Doyle-Edwards theory. And let's look at the shape of those predicted models. So the most commonly used molecular models surprisingly predict discrete relaxation spectra. We would expect that a material has a continuous distribution of relaxation times. But from the theoretical approach, we get the Gauss model where G is derived from molecular parameters, and the longest relaxation time comes from molecular parameters. And then all the shorter modes are scaled with a square of I, where I is the parameter going through 1, 2, 3, 4, summing up these modes. Now, the Doi-Edwards theory, again, for molecular parameters has a front factor and the longest time, and the weight here, the front factor, is scaled with this parameter I, and I is going 1, 3, 5, and all through odd numbering. So theory would give us a discrete spectrum, which is quite interesting. Now, one of the oldest attempts to get the spectrum was proposed by Tobolsky in 1959. He wrote the so-called wedge box model, where he said he has a spectrum decaying in time as such, and then after some shorter time, it stays constant. So this would be the box, and this would be the wedge. Now, the glassy behavior, the transition to the glass, is described very well by that type of scaling behavior. And I think that's a great success of the Tobolsky model. However, this box is not appropriate for describing the polymer melt in the entangled region. It required some modification. In fact, we did some work. I will describe this in a moment. The general description of a spectrum for a broadly distributed polymer melt, which might be also branched or so, is given by the transition to the glass, and then entanglement region, and then a broad transition and cutoff at the longest. So that's a typical feature which we would expect from experimental data. For the monodisperse polymer melt, where you have linear molecules which are flexible and all of the same length, you get a relaxation spectrum which is very simple. So that's the type you would get when you cook spaghetti. You know, you have a bundle of spaghetti in your hand, all of them of the same length, and then you cook them, and they're soft, and they're entangling, and they're forming a mass of long chains of uniform length. Now, at very long times, we will realize that the chains are of finite length, and there's a longest relaxation time. Beyond that, the material will be completely relaxed. But shorter modes are given by a self-similar spectrum. Somehow, the relaxation spectrum is the same at all length scales. It doesn't matter whether you look at the chain, the entire chain, or small segments of that chain. It relaxes in the same fashion. So it's a so-called self-similar behavior until you reach a shortest mode where you see then details of the chain. Maybe you're looking at bond relaxation and some angles. And then there's the onset to the glass. And this is the scaling behavior which is already known from Tobolsky's proposal. So that would be the glass transition. But those are typical spectra of real materials. Well, those down here, those are real materials. This is a hypothetical material. Also, those equations up here are not quantitative. When you compare the predictions from those models to experimental data, you'll find large deviations. They're able to model the flow region, but not the entanglement behavior, for instance. They're very large deviations. And now I want to address the question, how can we measure the relaxation spectrum of a material like that? The experimental procedure goes something like this. We measure the linear viscoelastic, we measure any linear viscoelastic material function. See, going back to the Boltzmann equation, you remember that the stress can be calculated if we know the relaxation modulus. And now we reverse that. We would say we make an experiment in the linear viscoelastic region. Can be any experiment which gives us the stress and the rate of deformation. And from those experimental data, we somehow evaluate the relaxation modulus. And from the relaxation modulus, we get the spectrum. So we are inverting that approach. We perform any linear viscoelastic experiment. Of course, we will pick the nicest one, the easy one, most easy one to do, the most informative one. To make the data accessible, we would pick a stable sample, which wouldn't change during our experiment. We would look for linear conditions, small strain behavior, and we would perform those experiments at a discrete set of temperature levels, because then we can apply the time-temperature superposition principle and extend our experimental window. We could shift data into each other. So the second step then would be time-temperature superposition. We would have to make sure that our sample doesn't undergo phase transition from going from one temperature to the other. So it has to be the same material. So this gives us the wider window. And from the data, we will determine the relaxation modulus and the spectrum. That's the general approach, independent of the material function which you are going to use. Here are a few experiments which have been used extensively. I listed them on the left side here as the experiment. And this is what we prescribe. Then in the middle is the measured result. And on the right side is the evaluation of the data. What will we get from the specific experiment? The first candidate is the step strain experiment, where the strain is suddenly jumped from 0 to a finite value and is kept constant from here on. The response is a stress, which is time dependent. We build up a stress when deforming. This stress is highest at first, and then it is relaxing. And in fact, the relaxation modulus is equal to the stress, the measured stress here, divided by the jump strain. So it's a direct measurement of the relaxation modulus within a time window, a shortest time and a longest time. Well, the longest time would be the duration of the experiment. The shortest time is given by the characteristics of the startup. There's somehow, you have to use some wild strain history to introduce the strain in the beginning. And for some time here, in the order of your startup time, your data will be hard to analyze. So you will not get the short time behavior from that experiment. It will not tell you the glassy behavior, for instance, of this material. You will find the rubbery behavior and the flow behavior in that system. So this is why there's a minimum time in this experiment. The next candidate is oscillatory shear, where a sinusoidal strain is inputted in the material. It's mostly shear because that's easiest to verify. The stress response is measured. It's also sinusoidal with the same period as the input. The data is reduced into a storage modulus and loss modulus in a frequency window between a minimum frequency and the maximum, depending on your instrument, so range of frequency. And from that, you can calculate the relaxation time spectrum. We will talk about this, how to go from here to here. So it's not as easy as up here, where we got the result immediately. Now, the spectrum is only valid between a minimum time and a maximum time, and the smallest time is 1 over omega max, and the longest time is 1 over omega min in the order of magnitude. So the time window corresponds to the frequency window. The transformation will not produce any miracles. Only you can only expect the information which you put in here transform to the information down here. We have to keep this in mind. Another popular experiment is this CRIP experiment. A load is put on the sample at time t equals 0, and this load is being constant from there on. The response would be shear, if you do that in shear strain, and the shear strain might jump and then gradually rise and then reach a constant rise time. It's basically a flow region, so the slope here is 1 over the 0 shear viscosity of the material. Now, the so-called compliance of the material, J, of t, the time-dependent compliance, is given by the time-dependent strain divided by the load. And this compliance is the inverse function of the modulus. So you have to invert the data to get the relaxation modulus, and from the relaxation modulus, you can calculate the relaxation spectrum. That's more involved, and you might wonder why anybody would do that. But one reason is that the time windows involved in this experiment, in the creep experiment, time window is different than the time window in dynamic mechanical, for instance. In a creep experiment can be performed over long periods of time. And the dynamic mechanical experiment is only performed in the frequency range which is admitted in the experiment, in the real experiment. So those experiments have complementary time windows, and you could calculate or you could determine the relaxation spectrum in either one of those experiments and then overlap the data and get a total spectrum over an even over an extended window. That's a future thing. It's very, I would say it's pretty much solved. The problem is solved here of this conversion. We can determine the spectrum from dynamic mechanical data. It is still very difficult to determine the spectrum from creep data for various reasons. You will see why this works out fairly easily. So the choice of those functions is arbitrary. You could also take a startup experiment, startup of shear. You could take, you could put your sample in the rheometer, start shear flow, and measure the stress as it grows in time, and analyze that stress in terms of a relaxation modulus and spectrum, and get your time constant in the same fashion. So it is really up to you. We will use the dynamic mechanical experiment where we put a periodic load on the sample. The advantages of such an experiment are the following. Let me list those very quickly. The first advantage is that the probing time is in the order of a period of that dynamic mechanical experiment. And this probing time is 2 pi over omega. So you're changing your probing time by changing the period of your experiment. The second advantage is that the startup time of this dynamic mechanical experiment is in the order of 1 or 2 periods, independent of the relaxation time of your material. If you have a material which has a long relaxation time, you still can do this dynamic mechanical experiment and get reasonable data. And the third advantage really is that we are probing the material with G prime and G double prime. G prime contains the spectrum by itself, and G double prime also. Both give a complete description of the relaxation modulus, but they're probing the modulus in different ways. And by combining those two functions, we have an easy time evaluating our spectrum. If you would just look at stress relaxation, you will get G of t. You have a single function, and you will have a hard time determining the spectrum from that single function. The same thing with J of t. And that's a simple fact, and we learned that the hard way. The classic people like John Ferry, for instance, when you happen to meet him, they knew this in the 60s. They knew that this approach is really much more powerful for determining the relaxation spectrum, and indeed it is. So this is where we will pursue things further. So we really want to get down to numbers. We want to have a spectrum. The first step to get good data, or the first step to get a quantitative spectrum is to have material data. We have to do a measurement. And here I brought a typical set of dynamic mechanical data, the input for our analysis. The relaxation is given by the storage modulus, G prime. And typical, we took a PDMS, simple PDMS, nothing really exciting. That's not the point here. We just have G prime as a function of omega, and also G double prime as a function of omega. And you can see already the shapes of those curves are different. We have several curves here because the temperature was varied between minus 60 and plus 180 to apply time temperature superposition. That's the first step. We will increase our frequency window by shifting the data so that we reduce them into a single master curve. The master curve would be represented at a temperature level T0, so G prime and G double prime would be reduced to a temperature T0, and we would have a shift factor up and down. This is the B of T, and then we have a shift factor for the frequency for those two. Okay, so this is our data, and we have to shift them in the omega axis and in the up and down axis. If you take the ratio of those two to determine tan delta, you realize that this function is independent of this front factor B of T. Right? So if we not only plot G prime and G double prime, but also tan delta, then we can separate the shifting in horizontal direction and vertical direction. Tan delta gives us the horizontal shift. That would be the first step to do. So we are plotting tan delta. And shift all the curves on top of each other. That means we shift all the curves so that tan delta is on top of each other, and this is done by shifting sideways. But you can see that there's still not an agreement between those curves. G prime and G double prime are not reduced to a single master curve. But you see that the frequency window is drastically increased by the time temperature superposition. What was my previous window here? Looking at the same scale, you can see from a small window like this, we increase to a large window. Now, the next step comes by shifting G prime, G double prime up and down so that they fit and form a pair of master curves, and this is the result. This is G prime, and this is G double prime. This is tan delta. Tan delta is not needed at that prime. We just can take G prime and G double prime. So the result of that shifting is a set of G prime, G double prime over a wide frequency window. And it also gives us the temperature dependence of the relaxation. We have AT. It's plotted here at 1 over T, because if it's a straight line here, it would be Arrhenius behavior. So AT is measured from the shifting, and then from the horizontal shifting, and BT is the up and down shifting, the vertical shifting. And this vertical shifting is very small. It's really, BT is close to 1, as you can see. But AT is a large, changes over a large region. And of course, AT is 1 at our reference temperature. So this is the result of the experiment. We should not trust the data completely. There's some problems in the experiment itself. Here, I assume that the data are okay. That actually, the analysis of the data will help us to go back to them later on and analyze the data in terms of their consistency, self-consistency. So we will have some information whether the data are agreeable. In the moment, let's take the data as they are. But even the shifting has a problem. The shifting, where's trying to find my, here, when shifting tan delta, from shifting the different tan deltas, there is a low region in the tan delta curve. And in this low region, we have very little criteria about sideways shifting. You know, it's really up to you whether you want to shift it a little bit to the left or a little bit to the right. And here we just went through the exercise and shifted as much as possible to the left and as much as possible to the right to see what's the possibility, what's the the slack in our data. And also we would like to see how does this affect then the master curve in G prime, G double prime. So we're getting different master curves in G prime, G double prime. Recently we do all of the shifting automatically. And I have a program where the shape of those curves is compared, and then the shifting is done automatically, and that tends to give even a better shift than the manual shifting which we're seeing here. So we will probably reduce this. If we have a good data set, then the automatic shifting will give us a better reduction of the data. But be aware of this problem. The shift factor itself also is affected by your choice of shifting. And here you can see there are some deviations. Here AT is plotted over temperature, not over 1 over T. That's why it has this type of shape. So we have to be very careful about about our input, about our way of treating the data. This makes much of a difference. After having gone through this, we have to rephrase our plan. We have data now in a wide frequency window, and we really would like to determine the spectrum. We haven't forgotten that. This is really our objective. This is what we are aiming. We would like to have the spectrum. And there are many, many different ways which have been proposed in the literature. One spectrum here is given by Ninomiya in Ferry. Here he has h of lambda. He has a slightly different notation, h of lambda. And A in this this description is just a constant fitting parameter which is between 0.2 and 0.4. And then he uses just G prime and G double prime evaluated at certain values of lambda. So those are evaluated at 1 over omega being equal to lambda. And this way you can pick certain lambda values and determine h of lambda as a continuous function. And the result of that indeed is just a conversion of G prime, G double prime into this plot which we are looking for. So this I'm writing tau here. So h log h over log lambda. So in 59, Ferry was indeed able to do this, but it's a complicated procedure, and we don't know the range of validity. We would like to have a method which is not based on an empiricism like that. We tested this method later on now, where we have more accurate methods, and it's really surprising how well it works. So it's very, very impressive. So we would like to have a method which is more self-contained, which is not, which doesn't depend on empiricism like that. And that's what I want to discuss with you next. The approach is the following. We are going to model dynamic mechanical experiments. We will model oscillatory shear. In this case, we take the Boltzmann equation, enter the sinusoidal shear here for the deformation history, and we also will take a discrete spectrum, a discrete relaxation spectrum for modeling the relaxation modulus. That's not a restriction in the approach, as you will see later, because we will be able to convert this discrete relaxation modulus into a continuous modulus. You can see already that if you place the modes as close, very close to each other, then there is a transition from the discrete modulus, from the discrete spectrum to the continuous spectrum. So let's stay with the discrete spectrum for the moment. We put in the strain history according to this here, and find that G prime is given as a sum of the contributions of the different Maxwell modes. The parameters are the Gi and lambda I from 1, where I goes from 1 to n. So those are the parameters which we would like to determine from our experiment, And the experimental input is a set of these curves, G prime, G double prime curves. That's our experimental input, and the output, if we are successful, is this parameter set down here, which we then can put over into the relaxation modulus, and the problem is solved. It's actually a quite nasty problem. It's I should tell you the story. We have worked on this conversion for quite a while, and we could do that, but it was quite involved. And a new student came here from Karlsruhe. His name is Baumgaertel, Michael Baumgaertel. And he bragged about his capabilities of solving this type of problems, fitting curves with many parameters under awkward conditions. And I thought this would be the right problem for him, because then he would be humbled and would be put down on the ground like everybody else. And I thought that would be a good lesson, really, for him as a student. But in fact, 2 weeks later, he came and he solved the problem. So we're going to talk about his solution of the problem in the following. And there was some hard work involved and some luck altogether, but only gradually we are finding out why this solution works and why it didn't work before, why we had problems all the time. So now I will try to point this out in detail. Now, we haven't analyzed this conversion in terms of mathematicians, so we didn't prove anything. But when you work with those spectra, you see ranges where problems are going to start, and you realize why those problems are coming in. And you pretty soon realize how you can avoid those problems. Okay, so let's follow the different steps. The input was given as a set of m data points. At m different frequencies, we had G prime, G double prime, and we could take our model now and compare the value of G prime as given by the model at omega k and subtract it from the measured value at omega k. So this is the data point, and this is the model prediction. And if Gi and lambda I are chosen in the right way, then this deviation will be small. So we are doing this for G prime and for G double prime, and summing up the deviations for all the m data points. And of course, we take the square deviation normalized with G prime and G double prime. So that's the problem to minimize. And we realize that the fit will be better if we take more and more data points, if we take more and more relaxation modes. If the number of relaxation modes is higher. If we take n very small, then the deviation will be very large. Let's say if we take just 1 or 2 Maxwell modes for describing the whole spectrum, it will be very wavy. But if we increase the number of modes, then the fit will be better and better, but it doesn't keep improving. At a certain level, the improvement is not significant anymore. And it stays about constant. It turns out that the deviation, the standard deviation, which we have at this level, is in the order of the noise of the data. You cannot improve the fit beyond the noise. So we don't choose any more modes in this case. We saying this is our optimum range. If we would choose more modes, we would try to fit the noise, and the problem would become ill-posed, and it would not work out. And that's where I always was working before, and I was having this ill-posed problem. But Michael somehow reduced his number of modes, and then he found a good solution. And this was really the key to his success. Let me break here for a moment. I'm getting a signal, so we should continue in a few moments and talk more about the details of that parsimonious model. Okay, very good. So the relaxation times are freely adjustable in this model. So that's a very important part, freely adjustable. And this allows the relaxation times to move to values which are needed for the material. We are looking for a relaxation spectrum which is characteristic for the material. Now, if we would say that we take a relaxation time for every decade or every half decade, and we would place that relaxation time at this specific value, then it certainly would not be at the position where the material is having a characteristic relaxation modes, and we would have to compensate the error we are introducing with one relaxation times, would have to compensate with another relaxation time, would make it very complicated. So by letting those relaxation times adjust very freely, Michael was looking for the typical spectrum. When doing that, he realized that relaxation modes tended to merge. Some relaxation times moved very close together, and the material told us that we don't really need so many relaxation times. They would just merge, and the number of times would be reduced. So we would be starting with a large number of relaxation times and then move into this optimum range and get a good set of for our spectrum. At very high values of the relaxation, high values of the number of relaxation modes, the problem becomes ill-posed. Let me discuss that a little bit about ill-posedness. The problem is something like this. We have a data set, G prime, G double prime. You have that somewhere on the back, but that's just look at this argument here. The data are limited to a certain frequency range. But our objective is to find a relaxation modulus over a wide time range, a range from 0 to infinity. So for the inversion, we really would need data over the whole frequency range, not just over a frequency window. So somehow the formulation of the problem is incomplete. And now what could happen is the following. If you take a data set, like let's say m data points, and you evaluate g of t for that data set, you get just one relaxation modulus. Now if you add one more data point to your set, you have a set of m plus 1, you would calculate a new value, g of t. And if that value, or a new function, g of t, and if this new function is completely different from your previous function, then you would say the problem is ill-posed. Or if you add some noise to this data and g of t is jumping around erratically, then the problem is ill-posed. Or vice versa, we will test our procedure by taking a set of data points later on and adding a few data points or subtracting a few points and putting in some noise, and we will check our solution procedure about this problem of ill-posedness. You will find that the conversion procedure is very robust compared to all those problems. So by using the Parsimonious model, the spectrum with the fewest possible relaxation modes, we are avoiding this problem of ill-posedness without following up why this happens. I guess it happens because we don't try to model the noise of the data. We stop putting in more and more modes at the point where we start jumping around with the noise in the data, and that would make the problem, of course, ill-posed. We are avoiding this in the Parsimonious model. Now, how does a typical fit look like? I thought I had a typical data set. Yeah, this is a typical data set coming out as one of the first sets calculated by Michael. We took data on from the literature, data on a polystyrene. It's a bimodal distribution of blend of two narrow molecular weight distribution polystyrene from Schausberger. And you see the data points here. And the line going through those data is the fit. Now, this fit for G prime here, I'm drawing this fit here, G prime, is modeled by the discrete relaxation modes. This is the longest mode. And the next mode, you can see that the longest mode really carries the spectrum here to the lowest frequency. And each of those modes has a breakpoint which is at a frequency 1 over its characteristic time, 1 over its Maxwell time. You know, every curve like this is one as a single Maxwell mode. So that's where it has its break. And somehow the total curve is carried as a sum of all those contributions. Now G double prime is also a sum curve. This is the sum of all the modes here, but the local description is different. Mode 1 carries the curve really in the neighborhood of here, and 2 carries it locally here. Mode 1 will not carry any part of this curve over on this other side. So the Maxwell modes in G double prime carry locally only. Therefore, and that's the that is the third advantage. Remember the advantages of the dynamic mechanical experiment, one probing short times wherever you want them, having short startup times. And this is the third advantage, probing your spectrum in different ways when looking at G prime and G double prime. And now we are picking up on this advantage by choosing Maxwell modes in our discrete spectrum, since the Maxwell modes is supporting the spectrum differently for G double prime and G prime. And in the curve fitting procedure, we are fitting this curve simultaneously with that curve, and that makes it a very robust fitting procedure. And I think that's why it works so nicely. Okay. From that, now having determined the spectrum, we automatically have the relaxation modulus, because remember the relaxation modulus is given as the sum of the Maxwell modes, Gi e to the minus t over lambda I equal 1 to n. And we can calculate now, without even having the relaxation modulus, you can calculate the relaxation modulus as the sum of those terms. Now, when looking at the effect of those different modes, I want to discuss another method of determining relaxation spectra, and that goes back to Tobolsky. It's called the method X. It goes something like this. Note that the longest mode describes G of t at long times, at very long times. And there it's the only mode which is fitting this curve. So imagine you have data G of t. You could fit the longest tail of that data set with your longest Maxwell mode. And from that you get a G1 and a lambda 1. You get the first Maxwell mode from that. And having that first Maxwell mode, you do the following. You take your data, say this is G of t data, and you subtract the longest Maxwell mode. This is G1 e to the minus t over lambda 1, right? And then by plotting this curve here, you would get a G of t, which is now carried by the second longest mode, because you're subtracting all those long parts out. And you can model now this, again, the long time tail, and you get mode, Maxwell mode number 2. And then you can unzip the spectrum by continuing getting mode 3, 4, 5, and 6. It looks very nice on paper, and if you have good data, it also is successful, but it very much depends on the quality of your long time data. And transducers are often weak at long times. So there might be an error at long times, which then propagates through your spectrum. So that's a difficulty in that method. But you can see very nicely how the spectrum is really decomposed in the individual modes. Now, having the relaxation spectrum in terms of modes, we can calculate any other viscoelastic function in the linear range. We can calculate creep behavior, for instance. This is the set of lambda i's at, here those are the lambda i's. Here, well, this is the gi at a certain lambda I. So these data points give us the discrete spectrum as calculated before. And from those, we can calculate now the retardation spectrum. There's a one-to-one correlation. The retardation spectrum you would measure in a creep experiment where you measure J of t, and the time dependence of the compliance is given by the retardation time spectrum. I didn't spend much time on the definition of the retardation time spectrum because it's nothing new. It doesn't contain any additional information. It might have a different weight on the relaxation modes, but if you have the relaxation time spectrum, you can calculate the retardation spectrum as done here, and you can calculate now the creep compliance, and you can calculate, for instance, the creep compliance at long times, which is given by the viscosity, zero shear viscosity, and you can calculate the individual contributions to the creep compliance. That's all set, and the mathematics for doing that has been developed in the 50s. You can find that in numerous textbooks. Simply, you could model the creep experiment. You could take the Boltzmann equation, you model the creep experiment, put in a jump in the load, and calculate the time-dependent strain, the strain response, and you will find this type of a response given here. Those h's, by the way, are Heaviside functions. Those are unit jumps. So for modeling this, you could determine now the retardation times, having gi's, lambda i's, and the constants in this derivation are also given. Here you have those in the handouts, but I don't want to go into the details. You can calculate those constants. It's quite involved, but since you will put this on a computer, you're not really bothered by all of this. So if you have the relaxation time spectrum, you can calculate the retardation time spectrum. People might not believe that. Actually, we thought, why not check our procedure by corresponding with somebody who did lots of creep experiments like Schwarzel. Schwarzel in Erlangen. He sent us a sample, a polystyrene sample. We performed G prime, G double prime experiments at a variety of temperatures and the time temperature superposition. So this is the G prime, G double prime as a result of that. So we have G prime, G double prime, and then from that calculate the creep compliance and compare to data. Professor Schwarzel also sent us his data, which he measured in the creep experiments. And indeed, the creep compliance, which we're calculating from dynamic mechanical experiments, is really identical with the creep compliance he measured. Now, creep experiments are quite involved, and several research groups had lots of developed instruments over a long period of time to measure creep compliances with that accuracy. Now, in our case, we used a commercial rheometer to measure G prime, G double prime, and just converted data. And this was actually done by a first-year graduate student, doing dynamic mechanical data. It was quite amazing how easy it is to go back and forth between spectra data and experimental data. So this was very nicely encouraging. That's very encouraging. Now let's look at this problem of ill-posedness. That's very interesting. In a real experiment, nothing is perfect. The signal in the dynamic mechanical experiment will consist of noise. You will have some wild behavior on short scale, time scale. So this will be some random noise, hopefully on very, very short frequency. And then there will be the probing on intermediate frequency. This is supposed to be a sine wave. This is the sine wave of our experiment. And from that, we are planning to get G prime, G double prime. And there will be trends in the material if the sample is not stable, if it undergoes a cross-linking reaction, or if it degrades in time, or things are happening to the material. So hopefully those trends are very, very slow, much slower than the probing time in this experiment, so that we get reasonable data for our material. So that's the range we are operating in. But let's see what noise will do and any harm will do to our data. We will take a nice data set. Actually here, this is a fairly peaceful set of data. It's just G prime, G double prime, fairly harmless curve, and it's converted. We calculate the spectrum, the GI values for certain lambda values. So this is the spectrum, and this is the retardation spectrum here of those points. By the way, those curves are not supposed to go through the data points. The curve here is G of t, the relaxation modulus, and this is the discrete spectrum. It just happened to go kind of parallel. And the same thing for the compliance, which is drawn here, and the retardation spectrum. Those points should not be on top of each other. But this is just the fingerprint of the material in the beginning, and now we put some damage to this material data set. We put random noise on top. You see those data are really horrible. When data from a conventional rheometer or from a commercial rheometer are normally much nicer. If there are any problems in the data, then there are systematic errors, not the statistical error. But we put a fairly large noise on top of the data and still modeled it with the Parsimonious model. Have just a few relaxation modes. And the modes will not follow all the noise, and they're pretty much the same as we had before. In fact, I could take the old spectrum. Here, this is the new one, and I put the old spectrum on top, and you will see hardly any difference. So by fouling up the data with this type of noise, we don't hurt the conversion method very much. It's a robust conversion method. It's certainly not an ill-posed problem. Let's do some more damage to the data and see what happens to our conversion. We will thin out the data set now. We just take relaxation modes. Here we just we just take our data points from our set here, and then we calculate relaxation modes from that. And the modes are slightly different. They're spaced a little wider, but when you compare them with the original data set, see, even those modes are, well, they're a little different, but not much. So the description of the data is, again, fairly unchanged from the data density. And we use that for reducing our data now. We change the data density. Let's say you have a data set which by time temperature superposition becomes very dense in a certain frequency range and very open in another range. We would reduce the data density in that dense region to make it kind of uniformly distributed, and then convert the data from here. Okay, so that works quite nicely. Let me discuss another point which you might be waiting for, the transition from the discrete to the continuous spectrum. And that goes something like this. We will be lumping some relaxation modes into Maxwell modes. We are lumping some parts of the relaxation spectrum into the Maxwell mode. That's actually the second handout which you have. It's a separate set of notes. Okay, so for a spectrum, which we, for the moment, for the time being, assume we know. For spectrum, we would take a range near lambda I, and we would try to lump the contribution in the vicinity of lambda I into a single mode. And that goes something like this. We would say that the relaxation spectrum, G of t, is given as an integral over the spectrum here. Now, the relaxation times are counted from the long ones to the short ones. So we will here have an integral from lambda I plus, here this is the lower, this is the boundary with a lower time, to lambda I minus, lambda I minus, and this is given by the relaxation module, by the relaxation spectrum times e to the minus t over lambda, d lambda over lambda. And we will do this not only for this interval, but we will do this for all the other intervals. So we sum this over n intervals, n time intervals, so that we cover the entire spectrum from left to right. Okay, so we're just summing up those integrals. Now, with lumping before, I mean that each of those contributions will be set equal now to a Maxwell mode. So this will be equal to gi times e to the minus t over lambda I, a Maxwell mode which is assigned to this lambda I. Now note that this range will be very, very small. We will have fairly fine steps for our integration. And if this is very small, we can say that h of lambda is not changing very much in this short time interval. And also e to the minus t over lambda is also not changing very much. And we could just say this is h of lambda I times e to the minus t over lambda I. Right? And we can put this outside the integral, since that would be constant. So we put this outside the integral, and we have now h of lambda I times e to the minus t over lambda I times this integral from lambda I plus to lambda I minus of d lambda over lambda. And this is equal, if we leave off the summation, actually the summation here was, of course, I from 1 to n, the same number of Maxwell modes. So this would be equal to gi times e to the minus t over lambda I. And you see immediately that the exponential function is canceling here. And also, you could evaluate this peacefully, and you will find that this is given by the natural log. Here when you integrate, you get the natural log times lambda I minus 1 divided by lambda I plus 1. And we will call this actually ln, we call this ln A. Okay, A is then, is a character, is giving us actually the spacing. So the result of that calculation now is that h at lambda I is equal to gi times the natural logarithm given by the spacing. And this is the relation which we will be using. See, you could now invert this. You could say from our conversion mechanism from before, we will determine gi's and lambda i's, and we can plot now h of lambda by saying here this is log lambda and this is log h. We could say we pick a certain value of lambda I, and then we write down gi times lambda times log a, and from that we will find then our our spectrum if we do this now for different points. Okay? So with that procedure, we will go back and forth between the discrete and the continuous writing, provided that the spacing is fairly small. If the spacing is very coarse, you will introduce an error, but that's natural. The question is, how close does the spacing have to be so that you still can get good data? Here's a typical data set where we produced that. We took 3 types of polypropylene melts. They are fairly broadly distributed. Have G prime data for this polypropylene. We have G double prime data for this polypropylene. By the way, the line going through this data is given by the parsimonious model, by the discrete set of relaxation modes. Note that we don't really have any waviness. The modes are close enough so that we don't see waviness, so it's a very nice fit. But we also put a continuous function through H after having calculated it, and then fit it with that continuous function, and it's about the same fit. Here you see the spectrum which we calculated. This is H for the three polypropylenes, and the points here are the discrete values of GI multiplied with, it's divided by, excuse me, yeah. So in my previous formula, actually here, I should have, I don't know, I left my formula. It's dug under in the meantime. Has to be divided by. Yeah, since we put this here, yeah, has to be divided by ln A, right? So we're dividing by ln A, and we use a spacing which is locally varying because we have freely adjusted time constants, but the variations are not so big. And you can see that those data points fit very nicely on the continuous spectrum. Now we can look at the effect of the spacing. We can calculate G prime, G double prime for the continuous spectrum, where we draw a line through here, continuous line. You can fit this with a continuous function. And we can take the parsimonious modeling with a certain spacing, and you see some waviness around the continuous representation. In fact, we use that to check the waviness of our response, the waviness of our calculated spectrum. So far, on the scale of my plotting, you didn't see any waviness in the results. But there must be some waviness because we're using a discrete spectrum. So how big is that waviness? We plot the deviation of the continuous G prime, G double prime. Or let's say the deviation of G prime calculated from the continuous spectrum versus the G prime, G double prime with the discrete spectrum. And you will find that if the spacing is very small, if log A is 0.3, you will hardly see any waviness. And if it's 0.9, it's getting bigger, here the waviness. And this is the waviness in G prime, and it's in G double prime. And you can see that the artifacts are larger here at low frequencies, and somehow in the transition from the flow to the entanglement regime, the fitting is more affected by the spacing of the relaxation modes. But if the spacing is reasonably small, and that's what we are choosing, the parsimonious model, you have hardly any waviness in the data, and there's no problem. We actually went back to the parsimonious modeling. In this case, we placed our modes now again closer and closer, and we found that the fitting somehow levels off. It's in the order of the scatter in the data. But then, I don't have this plotted in this case, but then we took a set of G prime, G double prime, which was calculated continuously without using the discrete modes. And indeed, when you take more and more modes, in this case, the fit gets better and better and better and better. So from that analysis, we can see that the lack of fitting is really due to the scatter in the data. And if we have perfect data there, there would be no problem in the scattering. We could evaluate the testing. We could evaluate our procedure now by doing the following. We take an arbitrary spectrum, a spectrum where we know GI and lambda i's. We take those for n modes, and we calculate G prime, G double prime. And there's no noise on the data. This would be a perfect data set. It would be unrealistic, but it would be an ideal data set. And with that, we calculate now, with our regression analysis, a set of GI lambda i's. We would calculate our discrete relaxation modes. And those modes then are compared with our initial data set, and then we can say whether the cycle is closed, whether our analysis is going to work. Now let me give you quickly two examples. One example is using a spectrum here where the GIs are weighted as listed here, and the lambda i's are spaced just one per decade, very coarse spacing. And in a second spectrum, we take everything the same, but the center mode is split into a mode which is a little shorter and a little longer. We're splitting this up. And now we're calculating G prime, G double prime for those, and use Michael's reduction method, calculating the spectrum. And indeed, both spectra are recovered by his method, and you can see in the center region small deviations between the two cases. So if we would have a data set without noise, our reduction procedure would give us exactly the real spectrum of that material. Okay, so it really follows everything in detail. But in actuality, we have noise, and we have to account for this noise. So that's fine. But note the waviness here. This waviness in the data is due to our artificial spectrum. It's not due to the reduction thing. Another extreme case, I'm done in a moment, but I just want to bring this to a conclusion. So another extreme case is shown here. We take a spectrum which consists of just two modes. It has a long mode and a short mode, and we calculate G prime, G double prime data points in a reasonable frequency window. We use the automatic curve fitting, the reduction, and due to this parsimonious modeling approach, where unnecessary relaxation modes are merging with other modes, all the modes in between are disappearing, and we end up with just two relaxation modes. And you see the line of the spectrum going through there. We're just recovering the spectrum as it is. And this would be G of T, here the relaxation modulus. You can see how unrealistic that is, but the reduction method doesn't care about realistic or unrealistic. So in summary, we can say that a discrete representation of the spectrum will give reasonable results if we have about 1.5 modes per decade. If we leave the modes free for the fitting, if we don't prescribe the relaxation time specifically, then the material characteristic modes will be calculated in this procedure. So we will discover the patterns in the material, the relaxation patterns, and that's what we are after. So we will find those in our procedure. And noise or thinning out of data or things like that don't disturb the relaxation, the evaluation procedure. We will get good results even if we have some noise in the data or some other problems. It's a very robust conversion. Thank you very much. That's the conclusion. Next time we can do some model calculations with that.